Get started. How's everyone doing? Doing good, I hope. All right, so today we're going to talk about some trig derivatives to start, and then we're going to talk about rates of change, and then the product rule. Okay, so some announcements before we do any of that. Remember, homework 3 is due on Monday by 11:59. You won't need anything you learned today on the homework. So just so you know, you have everything you need already to do the homework. But do let me know if you have any questions. I am going to be canceling office hours today, but if you email me, I'll respond as soon as I can. And I'll also respond over the weekend to any emails. Okay, so, but no office hours today. Keep that in mind. Okay. All right. Do we have any questions before we start? All right. So last time we talked about the power rule, and that's one of the rules you're going to use most often in calculus. Okay. And who can remind me what the power rule says? If I want to take the derivative of x to the n, then that is equal to what?
N times x to the n minus 1.
Perfect. N times x to the n minus 1. Wonderful. So that's the power rule. Today we're going to be first covering some trig derivatives and then real life applications of the derivative. Okay, so we want to find the derivative of sine of x. So to do this, we need to evaluate the limit. The limit as h goes to 0 of sine of x plus h minus sine of x all divided by h, right? This is the definition of sine of x prime if it exists. Okay, so in order to do this, we're going to need to use a trig identity. Okay, everybody loves trig identities. So we're going to use the sine of a sum of angles is equal to this thing on the right here. So sine of x plus h is equal to sine of x times cosine of h plus sine of h times cosine of x. Okay. Where does this come from? Well, it just comes from geometry, really, just drawing a triangle with the specified angles and then chasing it down. So if you want to see a proof, I can show that to you later. But you're not going to really need this identity very much in Calc 1, just so you know, other than to show that the derivative of sine of x exists. So we're going to plug this in. All right, so the derivative with respect to x of sine of x is equal to, well, that's, again, the limit as h goes to 0 of sine of x plus h minus sine of x over h, okay? And so now I'm going to replace this with the trig identity, okay? So this is equal to the limit as h approaches 0, okay? And then that trig identity says that sine of x plus h is sine of x cosine of h plus sine of h cosine of x. And then all that is minus sine of x over h. Okay, so I'm going to rewrite this. I'm going to combine this term with this term. Okay, so this is the limit as h approaches 0 of sine of x times, so both of those terms have a sine of x in them. So I'm going to do sine of x times, if I pull out a sine of x, I'm going to have cosine of h minus 1 over h plus sine of h cosine of x over h. Did I lose anybody there? I kind of did 2 steps at once. Everybody okay with that? Any questions on it?
Can you say that again for me, please?
Yeah, definitely. So yeah, I'll write it out in full detail. So delete. So I'm combining this term with this term, right? So this is, first I'll just write them next to each other. Sine of x cosine of h minus sine of x. So that's just me rearranging. And then plus sine of h cosine of x. So all I've done so far is just rearrange the top. Okay. H. All right, so now this term and this term both have a sine of x in common. So I'm going to pull the sine of x out of that term. So this is the limit as h approaches 0 of sine of x times, well, when I pull sine of x out of here, I'm just left with cosine of h. When I pull sine of x out of here, I'm just left with minus 1 plus, all right, and then plus sine of h cosine of x over h. All right. And so then everybody okay with that? Okay, so then this is going to be the limit. I can just break that into, this is a limit of this thing plus this thing, right? So I can break it into 2 limits then. You can break this into the limit as h approaches 0 of sine of x times cosine of h minus 1 all over h plus the limit as h approaches 0 of sine of h cosine of x divided by h. Did I lose anybody there? Okay, so sine of x right there, that doesn't have any h's in it. So I can just, with respect to the limit as h goes to 0, I can just pull it out in front of the limit. It doesn't depend on h, so as far as the limit is concerned, it is a constant. Okay, so I'm going to just say this is sine of x times the limit as h approaches 0, cosine of h minus 1 divided by h. And then over here, the same thing. Cosine of x doesn't have any h's in it. And so as far as the limit is concerned, the limit is as h goes to 0, cosine of x is a constant. We know it's not actually a constant. It depends on the variable x. But the limit only depends on h. So I can pull that cosine of x out in front. Okay. Questions so far? All right. This is a special limit that I didn't teach you guys, but we'll later see that this limit is actually equal to 0. Okay. This limit here, I did show you. Who remembers what that limit is? This limit is equal to 1. Okay. So then, the definition of the derivative tells us that I'm left with 0 times sine of x. So that's going to go away. Plus 1 times cosine of x. And that's just equal to cosine of x. So all of this work showed that the derivative with respect to x of sine of x is equal to just cosine of x. Very important. Okay. Are there any questions on that? Any steps that need clarified other than maybe saying that that limit is 0? Okay, so if I want to find the derivative of cosine, you use almost the exact same process. You use a slightly different trig identity. And when you run through the definition of the derivative, you'll actually end up with the derivative of cosine of x is negative sine of x. Okay. And so to prove this one, if you're looking at the limit as h approaches 0 of cosine of x plus h minus cosine of x divided by h, because this is the definition of the derivative of cosine of x, you're going to use the trig identity cosine of x plus h. This is equal to cosine of x, cosine of h, minus sine of x, sine of h. Okay, and that's where that's the key difference between these two derivatives is the different trig identity that you use. Okay, but other than that, is the exact same process. You're going to factor out stuff and then go from there. Okay. All right, do we have any questions so far? This is also going to be important to remember. Okay. All right. So later, when we have other rules at our disposal, we're going to learn about the derivatives of the other trig functions. So that's tangent of x, which is equal to sine of x over cosine of x. We'll learn how to take the derivative of this next week. And so we'll learn how to take the derivative of tangent of x next week when we learn what's called the quotient rule. And same way with secant of x, that's just 1 over cosine of x, cosecant of x, which is 1 over sine of x, and cotangent of x, which is cosine of x over sine of x. We'll learn how to handle all of these derivatives once we learn the quotient rule, which tells you how to take the derivative of one thing divided by another thing. Okay. All right, so for now, though, let's do some examples. Sines and cosines, that's enough to do some interesting problems, okay? So find the equation of the tangent line to the graph of the function f of x is cosine of x minus x at x equals pi. Okay. So if I back out of here for a second and I plot this in Desmos, so that we can get an idea of what it's going to look like, you go to functions, you go cosine of x. So there's cosine of x, and we're going to do cosine of x minus x. Okay, so this is the function we're looking at. Kind of looks just like cosine of x, but it's sort of been rotated a little bit. Okay, so we want to find the derivative at x equals pi, which is about 3.14. It's about there, the point in the middle of the screen. Okay, so that's where we want to find the equation of the tangent line. So what does it look like the slope should be? Should it be positive or negative?
Negative.
Yeah, negative. Thank you very much. Exactly. This is, it looks like a decreasing function there. The slope's going to be negative for sure. So let's go back to notability. I want to find the equation of the tangent line to the graph f of x is cosine of x minus x at x equals pi. So what two things, first of all, what's my final answer going to look like? Is it going to be a number? Is it going to be an equation? Is it going to be a picture? What's my final answer going to look like?
The equation of a line.
Yeah, it's going to be the equation of a line, right? So I need to find y minus y1 equals m times x minus x1. I need the slope and I need a point on the line, right? Well, what's the point on the line going to be? x1, y1. Or at least what's the x coordinate going to be?
Pi.
Pi, exactly. So we know x1 is pi. F of x1, which is f of pi, that's going to be the y coordinate, is equal to cosine of pi minus pi. And who knows what cosine of pi is? It's okay if you don't. We didn't work very much with the trig function values. So if I look at the unit circle.
-1.
Oh, perfect. Thank you. Yeah, cosine of pi is -1. Pi corresponds to an angle of 180, right? So on the unit circle, then your cosine is your x value. And at 180, 180 degrees, the x value there is -1. Perfect. So this is our y1, right? x1 and y1. So y minus -1 minus pi equals m times x minus pi. So now all we have to do is find m. And how are we going to do that? If I want to find a slope, again, what should be ringing in your head?
Derivative.
Yeah, derivative. Perfect. So I need the derivative of f of x, right? That's the only thing that it makes sense to take a derivative of. So f prime of x. Well, it's a difference, so I can take the derivative of the first part and then minus the derivative of the second part, right? So what's the derivative of cosine of x?
Negative sine of x.
Perfect. Negative sine of x. So when you're a small, dumb little trick to remember that there's a negative there is anytime you're taking the derivative of a trig function that starts with the letter c, the derivative has to have a negative in front of it, okay? So negative sine of x, and then what's the derivative of just x? What's the slope? If I'm looking at y equals x, what's the slope of that?
0.
Careful, because this is really x to the 1, right? There's a 1 up there. So think power rule.
So -1.
Yeah, it would be -1 times x to the 0. And x to the 0 isn't 0. X to the 0 is 1. Okay? So it's understandable to think x to the 0 is 0, but x to the 0 is actually 1. Okay? So then that's my derivative. So I need f prime of pi equals, well, does anyone know sine of pi?
Zero.
Perfect. You guys are on it. So I'm going to get -0, which is equal to +0, and then -1, which scientists guess is just -1, right? So we're getting a negative slope like we think we ought to from the graph that we looked at, right? So that's a good thing. So I'm just going to plug that in there. And my final answer, I'll distribute this negative here and here. I'm going to get y plus 1 plus pi is equal to -1 times x minus pi. And this is one of the only times that I'm going to advocate for going to slope-intercept form, because we're going to get some nice cancellation here. So I am going to distribute this negative. We're going to get y plus 1 plus pi is equal to -x plus pi. And so when I subtract pi from both sides, that goes away. I get y equals, subtract 1 from both sides, -x minus 1. Okay. If you left your answer like this with -1 here, I would not take off points. The only time I would take off points for not going from point slope form to slope intercept form is if I explicitly asked you to go to write your answer in slope intercept form. Okay, because again, both answers give you all the information you need to plot a point on the line, or plot the whole line itself rather. Okay. Are there any questions on this example? All right. I didn't need all that space. All right, so that brings us to rates of change. So the derivative, when we were defining the derivative, we were looking at the limit of slopes of secant lines to find the slope of the tangent line. So if the function we're differentiating is a function that determines distance as a function of time, and that's usually called a position function. Then the derivative of that function, well, let's just look at the slopes for a second. If this is time t and this is my distance s of t, I'm going to say s of t is in miles for this, miles, and I'm going to say that t is in hours. Okay, well, if I take a secant line through here, well, the slope is going to be, so this is, we'll call it a, and we'll call this a plus h. The slope is going to be s of a plus h minus s of a divided by h. So in particular, what units does the top have? S is in miles, so this guy is in miles, right? I'm just saying S at some time plus a little bit more time. That's in miles. S of A is in miles, so the top is in what? Two miles minus 1 mile gives me an answer that's in what? If you add two things and they have the same unit, what unit does the final answer have?
The same unit?
Exactly, it has to have the same units. So this is in miles, because we're saying S of t is in miles. This is in miles. So this slope of the secant line is in miles divided by, well, I said t was in hours, so that means a and a plus h are both times in hours, so h is in hours, okay? So in other words, the slope of the secant line, the units are miles per hour. And that's just a speed or a velocity, right? So when your function that you're taking a derivative of, when the function itself is a position function, and again, that means the function determines distance as a function of time, then the derivative with respect to the time variable is called velocity. And you can just think of it as the units, right? And we usually denote velocity as v of t. So v of t is s prime of t. Okay. Are there any questions about that? We went very silent. Let's look at an example. A ball is dropped from a height of 100 feet. The ball's height, s, as a function of time, t, is the position function. S of t is negative 16t squared plus 100. And here, s is in feet, obviously, because 100 feet, and t is in seconds. Okay. So I want to know, when did the ball hit the ground and how fast was the ball going the moment it hit the ground? Okay, so first, when did the ball hit the ground? All right, so this function, when I plug in t equals 0 seconds, it gives me the initial height of 100, right? S of 0 is 100.
At all. There was no banning people back.
So if you plug in some t that gives you, I don't know, let's look at s of 1. If I plug in s of 1, then s of 1 is 100 minus 16 is 84, right? So that says after 1 second, the ball, instead of being 100 feet off the ground, is 84 feet off the ground. Okay, so for question 1, I want to find t that makes s of t equal to what?
0.
0, exactly. So I want to solve the equation s of t equals 0. So let's do that. If I solve s of t is equal to 0, well, s of t is negative 16t squared plus 100. And by the way, this is a real equation that if you did this experiment, this would approximately tell you how high the ball was off the ground. This actually comes from physical applications, okay? Just so everybody knows. All right, so negative 16t squared plus 100 is equal to 0. All right, so how do we want to solve this?
We'll subtract 100 from both sides.
Perfect. Subtract 100 from both sides. Negative 16t squared is negative 100. Then what do I want to do?
Divide by negative 16.
Perfect. Divide by negative 16. I get t squared is equal to 100 over 16. Then what do I do?
Take the square root.
Take the square root. Perfect. I get t is equal to, technically, you should do a plus or minus, but we're talking about times here, and we don't really talk about negative time with these real world problems. So we're just going to take the positive square root for this problem, because if I took a negative, if I dropped a ball and it hit the ground in the past, that doesn't make any sense. So positive square root of 100 over 16. Well, that's the square root of 100 over the square root of 16, which is, the scientists guess, 10 divided by 4, and that's 2.5 seconds. Okay. Questions on that? All right, so I have the time that it hits the ground, t equals 2.5 seconds. Now, how do I find out how fast the ball was going the moment it hit the ground? And by that, I do not mean, I don't mean the answer is 0 feet per second. Everyone, when they first take this class, thinks that I mean when it has hit the ground. No, I mean the microsecond before the ball hits the ground. Okay, so how would I find how fast the ball was going in that split fraction of a fraction of a fraction of a second right before it hits the ground?
Plug in 2.5 into the equation.
Into what equation?
When you put S of t equals negative 16t, but you plug it in for t.
Careful. So we got 2.5 from solving S of t equals 0. So if I know if I plug in 2.5 into here, I'll get 0. So it's a good thought, but what was it?
The velocity equation.
Yeah, I need to plug it into the velocity, right? Because I don't want to know the height at 2.5 seconds. I already know that the height at 2.5 seconds is 0. I want to know the velocity at 2.5 seconds. V of 2.5. Well, V, this is a position function. V is just S prime of t, so S prime of 2.5. So what's S prime of t? When I take a derivative here, what do I get?
Negative 32t.
Negative 32t, perfect. So I'm going to get negative 32t, so negative 32 times 2.5. Again, that just comes from S prime of t for us is negative 16 times 2 is negative 32 times t. Okay. All right, so then that's what? Negative 64 plus 16 is negative 80. Negative 80 feet per second. Okay. All right, questions on that? So again, whenever I ask how fast was the ball going the moment it hit the ground, I do not want an answer of 0 feet per second because it's on the ground. No, I want the answer plugging in this time into the velocity. Okay.
How can it go negative 80 feet per second?
Oh, wonderful question. Let's draw what's happening here. So your book kind of glosses over this, but I'm not going to. Well, I was going to until you asked that, but I'm not going to now. So S of t, it all depends on just what you're defining as up or down. So we're defining, it makes the most sense to define in this graph down as down, right? So we're going to start with, the ball starts at 100 feet in the air, and then it comes, this isn't me drawing the path of the ball. This is me drawing the graph of S of t is equal to negative 16t squared plus 100. Okay. So as the ball falls, because we're defining down to be the negative direction, that's why this is a negative 16t squared plus 100. Because down is the negative direction, well, because the ball is traveling down, it's always going to have a negative velocity, okay? So all the negative 80 means, the fact that it's negative just means it's traveling towards the ground, not away from the ground, okay? And then these physical real world problems, you have to define, normally people define, yes, traveling towards the ground as the negative direction and traveling up away from the ground as the positive direction. And that's all we've done here. Does that help? Does that answer your question? So if we had gotten a positive velocity, that should have been alarming actually, because that would have said the ball is traveling away from the ground just when we dropped it, and gravity is broken.
So the negative sign just gives us the direction.
Perfect, exactly. The negative sign tells us, yeah, that's exactly what it does. And the velocity is actually later, if anyone takes Calc 3, then you'll learn about, maybe even Calc 2, you'll learn about what are called vectors. And velocity technically is a vector, which means it has a size. The size of this is 80, right? And for us, the direction just is towards the ground, which we're calling the negative direction. But yes, exactly. That's exactly what's happening. And so if I just ask for the speed, speed is the absolute value of velocity. So if I had asked for the speed of the ball right before it hit the ground, then that would be the absolute value of this, 80 feet per second. And so really, to be safe back here, I should have phrased the question, what was the velocity of the ball? What was the velocity of the ball? But excellent questions, and yes, excellent observation. It's just that the negative is just telling us the direction that the ball is traveling. Okay. Questions on that? Some people actually do prefer to define down as the positive direction, and then that throws everything off. I'm always going to take down as the negative direction. Okay. All right, so that brings us to the product rule. So we're going to touch on this week, and then next week we're going to get into the product rule and the quotient rule, and hopefully the big, the king of all derivative rules. Okay, what's called the chain rule. So let's pretend for a second that you didn't know the power rule, and you tried to differentiate f of x, which is x squared, and that's just x times x, right? Most people, when they want to take the derivative of x times x, and if they don't know the power rule, what would be your natural inclination to do here? Most people, I'm going to put equals in quotes because this is wrong. I'm actually going to even circle slash through it. Most people want to say, well, the derivative of the product, I can just take the derivative of each thing separately and then multiply them. They would say, you would get this. But this is wrong. We know from the power rule that f prime of x is equal to 2x, right? If I do this, which is wrong, I'll end up with 1 times 1, which is just 1, right? So the power rule, which we know is right, we proved it. The power rule gives us something different than our guess at what the derivative should be. So clearly our guess here is wrong, and we need to adjust what we do when we're taking the derivative of a product. Okay. So what should our new guess be? Well, I'm going to show you what the actual derivative is, and then we will prove it, hopefully, in the time we have left. So if f and g are differentiable, which means, that just means f prime of x and g prime of x exist, okay, then the derivative of f of x times g of x is, and I'm going to mix notation here, this is f prime of x times g of x plus g prime of x times f of x. Okay, so it's not just the product of the derivatives. You take the derivatives each separately and then multiply each derivative by the original other function. Okay, So that's the product rule. And let's prove it now from the definition. So this definition uses a trick that everybody hates, just so you know. But it is correct. So the derivative of f of x times g of x. This is the limit as, well, you guys tell me, this is the limit as h goes to 0 of what? So the derivative of some function remember? If I call this just one thing, if I call this z of x for a second, I'll replace this with z. What's the derivative of just z of x? What goes in this limit?
Gx plus h minus gx by h.
Perfect. Z of x plus h minus z of x divided by h. All right, so now I'm just going to replace z with f of x times g of x. Okay? So this second term doesn't change. It's always just whatever you have inside here. So minus f of x times g of x. This first term does change. So z of x plus h. That says everywhere you see an x, plug in x plus h. So I'm going to get f of x plus h times g of x plus h minus f of x times g of x all over h. Okay, so any questions about why this limit is this derivative? All right, so now here comes the trick. I'm going to say this is the limit as h approaches 0 of f of x plus h, g of x plus h. I know f of x is differentiable, so I would like to, what the idea is, I'm going to subtract f of x times g of x plus h so that I can factor out the g of x plus h and just be left with something that looks like a derivative of f, okay? But I can't just subtract this without adding it back, because if I just subtract this, I change the value of everything. So then I add that back, so I haven't changed anything. Okay. So this whole thing, I subtract something that I want and I add it back. Well, in the end, I've only added 0, right? So that hasn't changed anything. And then minus f of x times g of x all over h. But then here's so that was the trick, and here's why it's so magical. So this is the limit as h approaches 0. So I'm going to do this piece plus this piece. Okay, so in the first piece, we have f of x plus h, g of x plus h, minus f of x, g of x plus h, divided by h, and then plus, while I'm doing the limits, I can do the limit of the sum is the sum of the limits, right? So plus the limit as h goes to 0 of f of x, g of x plus h, minus f of x, g of x, divided by h. All right, what do these two terms here have in common?
G of x plus h.
Perfect. So this is the limit as h goes to 0. I'm going to pull the g of x plus h out in front. It does depend on h, so I can't pull it out in front of the limit, but that's not going to matter very much in the end. So limit as h approaches 0 of g of x plus h. So then I'll be left with here f of x plus h minus f of x divided by h. What do both of these terms have in common?
F of x.
Perfect. And that f of x doesn't depend on h at all. So I can pull that out in front of the limit. So I get f of x times the limit as h approaches 0 of g of x plus h minus g of x divided by h. All right, cool. So what is this? That limit should
G
look
prime
familiar.
X.
And what is it?
G prime X.
Perfect. This is g prime of x by definition. And we assumed g prime exists. Okay. And then what is that little bit right there? The limit as h approaches 0 of that stuff.
F prime of x.
Yeah, that's going to be f prime of x. So the only thing to be a little careful about is I'm looking at the limit as h approaches 0. For the first term, I'm looking at the limit as h approaches 0 of g of x plus h times f of x plus h minus f of x divided by h, right? So this is a limit of products. And so with limits, you can just break it into the limit as h approaches 0 of g of x plus h times the limit as h approaches 0 of f of x plus h minus f of x divided by h. With limits, limits do work just the way you want. The limit of a product is the product of the limits. So then what can we say about that piece? What is that? What would you guess that it is?
G of X.
Yeah, perfect. So the only thing to be careful about is in order to be able to plug in h equals 0 for this limit, g of x has to be, what's the word? In order to just plug in h equals 0, g needs to be continuous, right? To just plug in a value inside a function when I'm evaluating a limit, the function needs to be continuous. But g is continuous, and why? Does anyone remember? Because all I said was g is differentiable. So why do I know that g has to be continuous? Well, if g is differentiable, remember that differentiable was actually a more strict condition, right? Differentiable, just continuous means I can draw the graph without lifting my pencil, but I can have sharp points with a continuous function, right? But differentiable means you have to be able to draw the graph smoothly, and in order to do that, you definitely can't lift your pencil, right? So if g of x is differentiable, then g of x is also continuous. We proved that last time, okay? So that's why I'm able to just say that this limit is g of x, okay? So in the end, we have the limit as h approaches 0 of f of x plus h, g of x plus h minus f of x, g of x, all over h. This is the definition of the derivative of f of x times g of x. Well, we just showed that the first part in the limit, this whole first term here, was f prime of x times g of x, right? Plus, and then we showed the second term was f of x times g prime of x. Okay. And so that's exactly what we wanted to show. The product rule. This part, remember, this is f of x, g of x prime. Okay. All right. You can try these examples on your own. I'll cover them at the start of the next class on Monday. But do we have any questions before you head out? So I'll write the answer down for this one so you guys can see it and do it if you work on it on your own. So the derivative f prime of x here, you take the derivative of the first one, 2x, and I leave the second one alone. So 2x times cosine of x, plus then you leave the first one alone, x squared, times the derivative of the second one, negative sine of x. Okay, so this is the derivative for problem 1. So when you sit down, if you sit down and try and work these out on your own, that's the answer there. And I'll write these out before I upload the slides to Canvas. Okay. So do we have any questions before heading out? Cool beans. All right. Have a good weekend, everybody. Remember, my office hours are canceled today, but you can email me if you have any questions, and I'll get back to you before the end of the day, probably. Definitely by tomorrow, I'll get back to you. Okay.
Thank you.
Thanks, everybody.
Thanks.
Thank you.
Mhm.
You.